All right, so now we're just going to do a ton of examples with Green's and divergence theorem. And I'm going to really encourage you during these to put them on pause and do them yourself. And then you can check your answers when I put up the answers. But really, watching me do this is going to be pretty much like watching someone play soccer in order to learn how to play soccer. It's not going to help you unless you're actually struggling with it and trying it. So I really suggest that you actually try these first and then just use the videos as a way to check. All right, so I want you to find the outward flux through this box using two different methods. Put it on pause, try it both ways. It's gonna take a while, you got it, and then come back and check. Okay, so I made this chart because if you're gonna do it the long way, you actually have to do 6 different surface integrals. The good news about this particular shape is if you notice dA here, when you go project onto one of the coordinate planes, will equal ds. And so it turns out that really you just need f dot n, and this ds will be the same as dA. But that falls out here, you'll notice, because this denominator here, which is usually our Jacobian that comes from our surface integral, in all of the cases, this denominator will be 1. So I'm still including all that just so you can see, but you, if you wanted, could have just found the normal vector, dotted it with the vector field, and then integrated over the correct side. So just a couple pieces to point out. When you are finding the normal vector, we can just find it visually, so you don't really need the gradient here for this. But if you wanted to do it the actual way, I'm thinking of this as one level surface. And so if I write g as x, you'll notice the gradient of this is just I. And then I need to pick whether I do positive or negative gradient. In this case, I'm using the negative when x is 0 so that it points outward. My flux points outward from the box at each point. And so my n points outward from the box at each point. So that's why I'm choosing either positive or negative I, j, and k, depending on which side we're looking at. And then when you just end up doing f dotted with n, and recall we're doing it on each side. So one thing that may be helpful is let's look at this one particular, how we got this. I'm taking my vector field f, I'm dotting it with I, which is going to give me just xy. But I'm doing this along the side where x is 3. So I'm substituting in 3 for x, which is why I'm integrating 3y. And then I've projected onto the yz plane. And so I'm just integrating from 0 to 2, 0 to 5, and I get 30 along that side. You'll notice that the outward flux cancels on these two sides. It's 0 on these. And then lastly, I have when z is 5, which is the top, I do have net outward flux from the top. And I think you can see that pretty easily on this picture. It looks like the vector field is definitely flowing out of the top. As opposed to seeing like when x, actually it's kind of hard to see in the visual from the other sides, but you can at least see it's flowing out there. So I have net outward flux of 150 through the top, 30 through the side when x is 3, and that's going to leave me with a total net outward flux of 180. Now, this is a really long and painful way to do this, so I wanted to do it this way first so you could realize if you have a closed surface like this, and if your partial derivatives of each of these components are continuous, it's way better to use divergence theorem. It's just usually going to be faster. So let's find the divergence. I'm rewriting our vector field down here. The divergence, I'm taking the partial of this with respect to x, which is just y, plus the partial of this with respect to y, which is 0, plus the partial of this with respect to z, which is 2z, and I'm integrating over the entire box. And so I just get a pretty basic triple integral that gets me to the same outward flux.